Welcome again to the General Chemistry 2 class. This section is on acid-base equilibria and salt equilibria. This lesson is about solubility product constant. Let us begin. So, this is the part 10 for the subtopic of acid-base equilibria and salt equilibria. Objective. In this lesson, we will explain and apply this solubility product constant to predict the solubility of salts. So, let us recall what is solubility. So, solubility, if we recall, it is the amount of solute that can dissolve in a given amount of solvent at a certain temperature. Also, we learned that a saturated solution consists of a solute whose concentration is equal to its solubility. To make sure that a solution is saturated with a solute, an excess of undissolved solute must be present in the solution. The equilibrium established in the system is heterogeneous, since the reaction involves a solid compound ions in the aqueous state. For a saturated solution of an ionic compound at equilibrium, the rate of the dissociation into ions and the rate of crystallization of the compound are equal. For a saturated aqueous solution of an ionic compound, which we will refer to as salt, the equilibrium constant for the dissociation at a specified temperature is called the solubility product constant, or K with the subscript of Sp. The expression for the Ksp of an ionic compound is written in terms of the equilibrium concentrations of the ions produced upon dissociation. Like any equilibrium constant, the Ksp is constant for a salt at a certain temperature. In this lesson, we will deal only with the dissociation in pure water at 25 degrees Celsius. Consider a saturated solution of silver iodide in pure water. Its solubility equilibrium can be written as follows. The corresponding solubility product constant is given by Ksp equals to equilibrium concentration of silver ion times equilibrium concentration of iodide ion. As for the case of saturated solution of lithium carbonate in water, the solubility equilibrium can be written according to the following chemical equation. The corresponding solubility product constant is given by Ksp equals molar concentration of lithium ion squared times equilibrium concentration of carbonate ion. Note that the concentration of lithium ion is squared in the Ksp expression, since 2 moles of this ion is produced for every mole of the compound. Example number 1. Write the K expression for the dissolution of aluminum nitrate in water. So, solution. Aluminum nitrate has the chemical formula of AlNO3. Its solubility equilibrium is given by the following chemical equation. So, for every mole of aluminum nitrate dissociated in water, 1 mole of aluminum ion and 3 moles of nitrate ion are produced. The corresponding solubility product constant is given by constant is equals to equilibrium concentration of aluminum ion times equilibrium concentration of nitrate ion cubed. The ion product Q is the reaction quotient for the solubility equilibrium. It is similar to the constant, except that the expression is in terms of initial molar concentrations of the ions instead of equilibrium molar concentrations. Considering silver iodide as an example, the ion product can be expressed as Q initial concentration of silver ion times initial concentration of iodide ion. So, ion product can be used to determine whether a solution is unsaturated, saturated, or supersaturated. When Q is less than the constant K, Sp, an unsaturated solution is formed. When Q is equals to Ksp, a saturated solution is formed. That is, precipitation and dissociation are at equilibrium. When Q naman is greater than constant Ksp, a supersaturated solution is formed, and precipitation occurs until Q becomes equal to the constant Ksp. Recall that precipitation is a reaction in which a water-insoluble compound is produced by mixing solutions of water-soluble compounds. So, we will go to example number 2. A cuprous iodide solution contains 1.4 times 10 raised to negative 6 cuprous ion and 5.0 times 10 raised to negative 7 molar iodide ion. Determine if the solution is unsaturated, saturated, or supersaturated at 25 degrees Celsius. At this temperature, constant Ksp of cuprous iodide is equal to 1.27 times 10 raised to negative 12. Solution. Let us write the Q expression for cuprous iodide. From the chemical equation at equilibrium, note that cuprous and iodide ions are at 1:1 mole ratio. Thus, Q initial concentration of cuprous ion times initial concentration of iodide ion. Substituting the given concentrations, we get Q is equals to 7.0 times 10 raised to negative 13. So, the value Q is less than the given Ksp value for cuprous iodide. Thus, this solution is unsaturated. Now, molar solubility is the solubility of a compound expressed in moles per liter. For an ionic compound, the molar solubility can be calculated from the Ksp value. The diagram below shows an outline of calculations for determining the Ksp of a compound from the solubility and vice versa. So, example number 3, calculate the molar solubility of silver iodide in pure water given that Ksp is equals to 8.52 times 10 raised to negative 17. So, the solution. To calculate the molar solubility of the salt, determine the concentrations of the ions at equilibrium. If we let S be the molar solubility of silver iodide, The molar concentrations of silver and iodide ions at equilibrium must also be S. Substitute this in the Ksp expression for silver iodide. With this, Ksp is equals to a S squared. The equation can be rearranged to solve for S in terms of Ksp. Thus, S is equals to square root of Ksp. Plugging in the given Ksp value, we get S, which is equal to 9.23 times 10 raised to negative 9 molar. Then, this is the molar solubility of silver iodide. Example number 4. At 25 degrees Celsius, the Ksp of strontium iodide is 1.4 times 10 raised to negative 7. So A. What are the molar concentrations of strontium and iodate ions in a saturated solution of strontium iodate? And B. What is the solubility in grams per liter of the compound? So solution. A. If S is the molar solubility of strontium iodate, the concentration of strontium ion in a saturated solution of strontium iodate is S, while that of iodate ion is 2S. Since every mole of strontium iodate produces 1 mole of strontium ion and 2 moles of iodate ions. Express the Ksp value in terms of the molar concentration of the ions Ksp equals S times quantity 2S squared or 4S cubed. Solving for S, we get S equal to cube root of the quantity Ksp divided by 4. Substituting the value of Ksp in this equation gives us S equals to 3.055 times 10 raised to negative 3 molar. The underlined digit is the last significant digit, since the given Ksp has 3 significant figures. We will use the value 3.055 times 10 raised to negative 3 molar in the succeeding calculation steps to avoid errors on the final answers. The concentration of strontium ion is S, which is 3.06 times 10 raised to negative 3 molar, rounded off with 3 significant figures, while that of iodate ion is 2S, which is 6.11 times 10 raised to negative 3 molar. Now, for B, the solution for B, we need the molar mass of strontium iodate to convert the molar solubility to solubility in grams per liter. The molar mass of strontium iodate is equal to 437.42 grams per mole. To solve for the solubility in grams per liter, multiply the molar solubility by the molar mass. For the molar solubility, use 3.055 times 10 raised to negative 3 molar to avoid errors in the final answer. Simplifying the equation gives us 1.34 grams per liter. The final answer must have 3 significant figures, which is consistent with the given Ksp value. Given below are the relationships between Ksp and molar solubility of compounds with various cation to anion ratios. So, familiar the following table and its corresponding compound to KSP expression, cation and ion KSP in terms of molar solubility. So, for a set of compounds with the same cation to an ion mole ratio, the compound with the highest value of KSP is the most soluble compound in water. The one with the lowest value of KSP is the least soluble. Consider cesium periodate, copper 1 chloride, calcium sulfate, and thallium 1 iodide. They are compounds with 1:1 cation to an ion mole ratio. To arrange them in order of increasing solubility, they must be arranged in order of increasing value of KSP. Thus, the correct order is given by thallium 1 iodide, followed by copper 1 chloride, then cesium periodate, and lastly calcium sulfate. When the compounds are of different cation to an ion mole ratio, their KSP values cannot be compared directly to determine their relative solubilities. In the given set of compounds, lead 3 iodide has the highest value of KSP, but it is not the most soluble compound. Yttrium iodate, with the lowest KSP value, is the most soluble compound. Thus, in this case, it is important to calculate the molar solubilities from the KSP values to identify relative solubilities of the given compound. So, conclusion. To summarize, the solubility product constant KSP is an equilibrium constant corresponding to the dissociation of an ionic compound in water. It is related to the molar solubility of the compound. And that would be all for our topic part 10, solubility product constant. So now, let us proceed to the quiz. So, part 10, solubility product constant quiz. Number 1. Choose the equation that shows the KSP expression for the given ionic compound. Calcium carbonate. Is it A, B, C, or D? Select the correct answer. Number 2. Choose the equation that shows the KSP expression for the given ionic compound. A, B, C, or D. Number 3. Choose the equation that shows the KSP expression for the given ionic compound. Fe2CO3 3. Is it A, B, C, or letter D? Number 4. Choose the equation that shows the KSP expression for the given ionic compound. Number 5. Choose the equation that shows the correct relationship between KSP and molar solubility of the given compound. Let us proceed. Number 6. Choose the equation that shows the correct relationship between KSP and molar solubility of the given compound. Select the correct answer. Let us proceed to number 7. Choose the equation that shows the correct relationship between KSP and molar solubility of the given compound. Is it A, letter B, or C, or D? Now we have number 8. What is the molar solubility of MnIO32? Given that its KSP is equal to 4.37 times 10 raised to negative 7. Is it A, B, C, or is it letter D? proceeding to number 9. What is the solubility in milligram per liter of silver arsenate, which has the total molar mass of 462.52 gram per mole, given that its KSP is equal to 1.03 times 10 raised to negative 22. Is it A, or is it B, C, or letter D? And lastly, number 10. Which of the following sequences shows the correct order of compounds in decreasing molar solubility? So, kindly refer to the table on the left side of the screen. So, choose the correct answer. Is it A, B, C, or T? And that would be all for our topic for today on acid-base equilibria and salt equilibria, part 10, solubility product constant. So, I hope you learned something and kindly apply it. So, have a nice day and be like a proton, stay positive.